This next section, we're going to be looking at studying pressure. And pressure is defined as a force per area. For example, if somebody steps on you with sneakers on, steps on your foot with sneakers on, it will not hurt as much as if that person was wearing high heels, because there's so much pressure. The force is exactly the same. The person weighs exactly the same, but because the area of the heel is now much smaller on the high heels than on the sneaker, the pressure will be much higher. Examples of pressure that we run into is the pressure inside of a tire. You have to keep your tires at a certain air pressure. When you're underwater, as you go deeper and deeper in the water, you feel that hydrostatic pressure. You feel that pressure of water above you. We have here supposed pressure acting on the back of a swimmer's hand is 1.2 times 10 to the 5th pascals. And PA stands for pascals, and that's our units for pressure, is pascals. If we go to the previous, equation, we see that pressure equals force over area. That's newtons per meter squared, which is the same thing as a pascal. So newton per meter squared is the same as a pascal. So a realistic value near the bottom of the diving end of the pool. The surface area of the back of the hand is 8.4 times 10 to the negative third meters squared. So determine the magnitude of the force that acts on the hand. So pause the video and try this problem now. Using that equation we just learned, rearranged to be force equals pressure times area, and we end up with 1,000 newtons. We encounter air pressure every day. The atmospheric pressure at sea level is 1.013 times 10 to the 5th pascals, which is the same thing as 1 atmosphere. So atmospheric pressure at sea level is this number here, which is sufficient to crumble a can if the air inside is pumped out. So what happens here is if you take the air out of this can, all the pressure on the outside will crumble that can. We're now going to look at pressure and depth in a static fluid. We're going to look at fluids and what pressure acts on us. And the fluids can be either liquid or gas. If we look at a fluid like water, we see if we envision a cube of water, a column of water here, at a certain height h, the top of that column will have a pressure P1 in area A. The bottom of that column of water will have a pressure P2 in area A. The pressure, the force is pressure times area. So the force, this is a free body diagram for our situation. The force from the water above is here. We have mg, this is the weight of the water, the column of water. And underneath you have a force here, this force pushing up on that column of water, P2 times A. There's a pressure as you go deeper and deeper in the water, there's more pressure above you. Now, since this column of water, we think of this column of water as being an object. It's just sitting there, resting there in the water. That means all the forces have to add up to 0. So you have this P1 times A plus the mg has to be equal and opposite to the P2 times A. They'd all have to add up to 0. That P2 times A numbers, that force here at the bottom has to be equal to these two forces on the top. We have this equation here. Now if we rearrange that, we end up with P2A equals P1A plus mg. Now if we divide through by A, we end up with this. Divide this by A, we get P2. Divide this by A, we get P1. If we divide this mass by A, we get rho and H. Remember, density is mass over volume, so it'll be mass. Height divided by volume will give me area. That's our area that's been divided over. So this is our new equation here, P2 equals P1 plus rho GH. In other words, what it's saying is the pressure here at the bottom of this column equals the pressure at the top of the column plus G times the height of that column. So where this type of equation comes into play is when we look at things like a dam. Lake Mead was formed after the completion of the Beaver Dam in 1936. Suppose that all the water were removed except for a relatively narrow vertical column in contact with the dam. Figure 11.7b shows a side view of this hypothetical situation. So over here, we've taken all the water back here away and just had this narrow column of water, in which the water gets the dam has the same depth as in figures 11.7a up here. The Hoover Dam still be needed to contain the water in this hypothetical reservoir, or could a much less massive structure do the job? So pause the video and think about what that answer would be. The answer comes out that the dam for our imaginary reservoir would sustain the same forces that the Hoover Dam sustains, so it would need to be equally large. What happens is all this water back behind here is supported, it's weighing down this floor, holds up all this water. So the depth of the water is what makes you have to build a certain size dam. Not how much water is behind it, but how deep the water is. So it doesn't matter if there's a small amount of water or a huge amount of water. It's the height of the water that matters, or the pressure. Figure 11.8 shows the cross section of a swimming hole. Points A and B are both located at a distance h, 5.5 meters below the surface of the water. Find the pressure at these 2 points. Well, they will. It doesn't matter that they're in a straight line here. It doesn't matter that there's not any water here, that it's just land. It is the height, the h above the surface of the water, so they actually will have the same amount of pressure in both these positions. So we'll use the equation, and that's what this says here, is that the pressure will be the same. So we go ahead and use the equation P2 equals P1 plus rho GH. Our pressure is what we want to solve for here. That's P2. P1 is the atmospheric pressure. That's the pressure above 1.1 times 10 to the 5th Pascal. So that's this air pressure. Plus we have to add to it the water pressure, which is the rho GH. So the pressure here at point A is due to the air pressure up above plus the pressure from the water here above. And that's where the GH comes from. There's the water, there's the air. So the air is 1.01 times 10 to the 5th pascals. Density of water, gravity, and the height of the water is 5.5 meters. So we end up with an answer of 1.55 times 10 to the 5th pascals. Figure 1111 shows 2 methods for pumping water from a well. In one method, the pump is submerged in the water at the bottom of the well, while the other is located at ground level. If the well is shallow, either technique can be used. However, if the well is very deep, only one method works, which isn't. So can you go ahead and pause the video and decide which one you think it is? The answer is a ground level pump can only cause water to rise to a certain maximum height, so it cannot be used for very deep wells. A ground pump pulls air, which only causes a maximum outside pressure of the atmosphere. It is letting air pressure do the work. So it can only lift as much water as the air pushing down causes the water to be pushed up. So this pump could evacuate all the air inside here, inside the pipe. But the only way that this water will be pushed up is due to the weight of the air. So you can only have a certain, this air only weighs a certain amount, so you can only have a certain amount of water being pushed up. For here, this pump down here underneath the water will work better because all it has, what it's doing is pushing water up. And so it can just keep pushing water up. It doesn't rely on the air pressure to do the work. The pressure gauge is an interesting application of looking at air pressure. We have this tube, and we have this pool of mercury down here. This is a mercury barometer. And this area up here is empty. It's a vacuum. And so this weight of the air, this air pressure, pushes on the mercury and causes it to rise up in the tube. And depending on the weight of the air, the mercury in the tube will move up and down, depending on the weight pushing down on that mercury. If the air is heavier, if you have dry air and it's heavier, the mercury will rise up. there's moisture in the air, it will be low pressure and mercury will come down. We can use our equation P2 equals P1 plus rho GH with the mercury barometer as well. And the actual value for the P2 is the absolute pressure. That's the pressure on the outside of the tube. The gauge pressure would be P2 minus P1, the difference between the two pressures. That'd be rho GH. That's called the gauge pressure. So the two ways we've learned in this lecture that we can calculate pressure is by force acting on an object divided by the area that that force is being applied. And the second way we can define pressure is by finding the pressure due to a fluid is that pressure P2 equals the pressure P1 plus rho GH. That P2 pressure is just the pressure on the underneath end, let's say, and the P1 is up on top. So in this previous example that we worked on, we wanted to find the pressure, for example, down here A. That would be our P2, and our P1 was the atmospheric pressure up above, and the rho GH was the pressure due to the water.